right. Welcome everyone to the Vulkan stream. If somebody can, as usual, say something in the chat around, hey, the stream works, the sound is good, that would be great. So the agenda for today is as follows. We are gonna continue where we left off, what was it, a year and a half ago or so. And we'll take our code base that we wrote that uses Vulkan 1.0, 1. I guess 1.0, maybe 1.1, I forget. 1.1, and we are gonna migrate it to Vulkan 1.2, which is hopefully going to be relatively straightforward. So the plan for today, is well, we are live. So the plan for today is switch to 1.2. And the point there is to just see, hey, we are using a bunch of extensions, and if you haven't watched the super long, like 4-hour stream or whatever from a couple of weeks ago, you can watch it at some point later. But I was talking there about the fact that a lot of things that are actually really useful are now core in Vulkan 1.2, so they're not extensions. And it so happens that we use a lot of them, so we will switch to the core functionality. And our main agenda, our second part of the agenda is to try to use GPU buffer pointers. And again, I talked a bit about this last time, and I'll repeat some of what I said then today when we get there. But the plan would be, the second thing that we're going to do in preparation for that is we're going to merge all geometry buffers that we currently use into one. So we use like an index buffer, a vertex buffer, a buffer with meshlet data, maybe something else, I forget. We're going to merge all of this into one to make it easier for us to do the third step. And so the third step is hopefully we're going to switch to GPU side buffer pointers. And I'll get into why this is interesting closer to when we do so, but suffice it to say the main point would be to make the code that we have been writing all this time, or by all this time I mean like a year ago, a bit more future-proof in the sense that if we want to load more meshes, if we want to start unloading meshes, make the memory management for all of this a bit more dynamic, and this would help there. And also this is like an interesting functionality that generally isn't available in any other APIs, so that's going to be nice as well. So that's the plan for today. 1 and 2 should be relatively straightforward. I have never done 3 before as usual, so like we will figure that out. Hopefully it will just work, maybe it won't. Who knows? We'll see. Alright, so in preparation for the stream, I have and like if you're following along, you'll have to do the same. I've updated Vulkan SDK to 1.2. The reason why the stream is today instead of like a week ago is that Vulkan 1.2 came out 2 weeks ago, but the SDK was actually only available a few days ago. So now you can go to Lunergy Vulkan SDK, and you can download Vulkan 1.2, and it's all great. So that's the main thing that I've done in preparation. Alright, whatever. YouTube continues thinking that my stream is not good, but my stream is usually good, so it's fine. So, the other thing that I have done, but I've actually done this a while back, is I've installed new Nvidia drivers. I don't know if there's a stable Nvidia driver that supports Vulkan 1.2, but you can go to Nvidia Vulkan driver, this. Right, so there's a developer beta Vulkan 1.2 driver, which if you install it, you're gonna have Vulkan 1.2 support. So hopefully all of this is gonna work. So Vulkan 1.2 released 2 weeks ago. SDK came out last week, like this week basically, earlier this week. So who knows if any of this works, but we'll see. Oh, and the other thing that we have to do is we are using the Vulk library to load Vulkan functions for us, so we'll have to update that as well. I've updated this at some point a couple of weeks ago to hopefully support 1.2. I'm assuming that all works. So let's start with something really simple. Let's switch our instance creation to 1.2. And I'm assuming, all right. Yeah, so this is the new SDK that already supports 1.2. And we will have to check, but I'm assuming that the drivers also support 1.2, so we are going to be able to create Vulkan 1.2 device. Let's see. All right. All right, so we have our RTX graphics card. Maybe I should have ran the code that we had before that. But okay, so we seemed to have created Vulkan 1.2 device. That's kind of all it took, but obviously that's not the point, right? We are just using the same functionality that we used to use so far. So we still use all of the extensions, etc. And this is kind of the point of all of these Vulkan version upgrades. Like, you don't have to rewrite your code to support Vulkan 1.2. You just can. And so this is what we're going to do today. But as you see, we switched the versions around and it kind of just worked. So let me update Vulk while I remember this. Wait. Sort order is weird. Oh, this is a file, not a folder. Okay, never mind. All right. This was an emoji that clearly doesn't render in the old Windows command prompt, but we should now have, I'm not sure if we are actually, yeah, so we are gonna need some of these functions later on. Oh, and even some of these functions like right now. So now we should have new Vulk. And now we should be able to start actually converting some things to 1.2. Let's see if the code still works. Cool. So the main point of the exercise in the first part of the stream is that we use a lot of these extensions. So we use 16-bit storage and 8-bit storage to make sure our shaders compile, and we use draw indirect count and sampler min max. And all of these 4 extensions are now core, so we don't need these extensions. So we use push descriptors, which I was planning to remove them at some point because I was hoping push descriptors would end up in core, and it's basically clear they never will. So it's basically a deprecated extension as far as people are concerned, from what I understand. We still need things like mesh shading because that's still not part of Vulkan 1.1 anything, right? So let's do this. Oh, actually no, let's convert the shaders first. So Vulkan 1.2 comes with Spear V 1.5, and I don't remember what we use right now. For our shader compilation process, maybe I should have done this in Visual Studio. But we are gonna need some features of the new shader model as well for the third part. So I think we should just do this now. Let's see. Yeah, so we are currently compiling towards Vulkan 1.2. So we should switch this to this. I don't know if the shaders will recompile if I just do this. Okay, they will. So that also worked. I'm curious. Let me try to do this. If I go back to 1.1, aha. So this is good. as you can see, once we start using 1.2 features, we actually really seriously need 1.2 device, right? So we just used SPIR-V 1.5 for the shaders. And then if we try to load this under Vulkan 1.1, it says, well, invalid SPIR-V binary version for target environment, right? So this is validation layers correctly detecting that once we start using 1.2 features, we really need 1.2 device. All right, so now that the shaders have been converted as well, let's deal with these extensions. So one thing to note is that for all of the extensions and also for all of the Vulkan 1.2 features, we have to explicitly enable them for them to work. And so here we have this slightly scary code that builds these like chains of structs that enable all of this stuff. And so you don't have to do this anymore in Vulkan 1.2, but what you do have to do is do something else. So let me try to figure that out. I don't actually remember where. There's like some struct. Let me just look at this stuff. There's some struct that you can now use, this guy, to basically replace this chain of structs that enable all of the features. I think it probably replaces this guy. Oh, right. Okay. Yeah, so we were using, it's kind of weird, like the names of some of these things are weird. So we were using features to struct. And I guess we now need features. Oh no, we need both. Okay, okay. So basically what we need to do is we need to make another struct that replaces all of these guys. Well, both of these guys, I should say. Yeah, so I guess the code doesn't actually end up much simpler, but let's do this anyway. So this is going to be important because we need to stop using these extensions, right? And so for us to stop using these extensions, we need to switch to 1.2, and to switch to 1.2 features, we need to enable them. And so to enable them, we need this beautiful struct, VK structure type. I don't even know what it's called. Physical device, Vulkan 1.2 features, I guess. No. This guy. And inside that struct, we need to enable things that we use. So things that we use are draw indirect count. We previously were, oh, interesting. It previously was sufficient to just use the extension. Now we don't need to use the extension, but we still do need to enable this. So let's do that. And basically we need to enable everything that we use. So we use this guy. We use this. Let me just copy like all of this, and then we're gonna figure that out. So we do use this. We technically don't use this right now, but we might want to. And we don't use this right now, but we might want to. So I kind of want to just enable all three of these. We don't use atomics right now. We do use float 16 and int 8. So basically like these five roughly cover this stuff that we are using plus some more things that we aren't using yet. So this is all bindless extensions that I talked about this last time, like a couple of weeks ago when I did the Vulkan 1.2 stream. We are not going to use this today. We are going to be using something else. So that we do not need. I'm not actually sure what this, it's probably related to bindless as well. So we are definitely using this. And also I'm a big fan of this guy, so we are gonna enable that. Don't need this. Don't need this for now. Don't need this or this or this. We will have to use these, or at least this. So I might as well just enable this now. Don't need this other stuff yet. I don't even... We are not really using frame buffers much right now, so I won't enable this for now, but I will probably enable all of the other stuff. Okay, so this seems reasonable. Great. Okay, now all right, so presumably this is a good start. Like we have we are now using the Vulkan 1.2 features. However, right now probably our code won't work, or if it does work, it's not great. Let's see if the code works. I wouldn't expect our code to work, and I will... Okay, this is not great. So the reason why I didn't really expect our code to work is because we still use occasionally the functions that are postfixed with KHR, whereas instead we should be using something else. Oh. And this is core now. Oh no, this is not core because... Okay, never mind. Right, so this function we are now using from core, so technically we should be using cmd draw indirect count without a KHR suffix. And is that it? Really? Okay, it wasn't super exciting, I guess. Huh. What? Wait. I'm slightly confused. Our code just worked, right? Wow. Okay. Now I'm using the non-KHR function. And our code still works. What? Uh-huh. Our code seems to randomly break now. Beautiful. Interesting. So this is saying... Alright. So congratulations, we have a Heisenbug. Occasionally when we run the code, and I guess we are now going to spend time debugging this because, you know, why not? I don't know. So we have a Heisenbug, and I don't know, I haven't run this code in forever, so I don't know if this is related to the... to the stuff that we've done just now, or if this just was like that before, right? But so what we have right now is that when we create the compute shader, let's see, this guy, right? Interesting. So it's not even when we create the shader, it's when we create the pipeline with the shader for... It's basically the first pipeline that we ever create. Then what happens is that the validation code runs over our shader code and says that something is not valid about this shader code. Okay. So the way you usually debug things like that is that the SDK comes with validation source. And so what we are gonna do is find that source. Spear v tools. Okay. So this is that. And try to figure out what's going on here. So we have an opcode that the validator doesn't recognize in the input stream. But only occasionally, right? Like it's weird. It's like occasionally when we run the code works. But then occasionally it doesn't. And so that's gonna be fun. Let me... Oh, great. The SDK doesn't come with validation source code anymore. So that's not convenient. Unless I mistyped something. Yeah, okay. That's a shame. It used to be the case that the SDK included the sources and for the validation layers, and now it doesn't. Okay, so there's a few possibilities here. One possibility is our shaders just randomly break on disk. Maybe like they are being recompiled occasionally, or maybe, I don't know, maybe I have a virus on my system or whatever. Or it could be that our code is broken, like our code doesn't correctly feed the program to the compute pipeline, which seems weird. I mean, we haven't touched this code for a year, but we've never had bugs in this. We don't even use a pipeline cache. We've never had bugs in this code before. And the third possibility is that there's a bug in validation layers somehow. I'm slightly surprised that it even validates like where it does. I need validation sources because I will not be able to figure out what's wrong here. So, all right, that was not expected, but let's see. So first, let's see if anybody filed an issue like that. Ah, no. Doesn't seem so. Okay, so let's do this. Let's instrument our shader loading code first to say, let's see. Okay, so whenever we load the shader, we will say loaded shader from path with length bytes and hash something. Path length, and then we're gonna use some standard hashing function. I'm not. Is there like a range hash? Oh, this is. Oh my god. So the hashing facilities in the standard library are kind of not like, how do I put this, not very expansive and not very easy to use. So maybe there's nothing that will help us here. Let's see. There's hash array. Where is this used? I'm just gonna like call this internal function because I don't wanna deal with this. Is that where the function is? Yeah. And so we're gonna hash the buffer with length, and it's gonna return size t. So we're gonna cast it. Okay, so this will tell us, are we loading the same shader when it breaks and when it doesn't break, or are we loading different shaders? So right now the code works. Now we need to run it up until it breaks, right? Like, since it doesn't break every time. Okay. So now it's broken. Okay, and of course the hash is exactly the same. So this strongly hints at the possibility that we aren't doing anything wrong. And note that I'm recording the shader right before I pass it, I think, to the validation layers. Recording the hash, sorry. Let's see again, where did I put this? It's basically right after I create the shader module, so like, I mean, maybe it changed in transit, but this seems unlikely. Right? So this works. I mean, it's so likely to be a bug in validation layers, it's just a really scary bug, right? It's like, yeah, okay, so the hashes are the same, of course, before and after. Okay. So this means that it's not a bug with our build system, it's not a bug with like the file open or file read or anything. We are feeding the same SPRV data to the Vulkan SDK, and then something goes wrong somewhere. Okay, so now I need validation sources because it's going to be impossible for me to figure out what is going on if I don't have them. And I'm just going to clone them here. We are off to a great start. One thing I might do, I so don't believe that this is a bug in our code. Like, it's impossible. Well, it's not impossible, but it's so unlikely. So one thing I might do is there's a way to disable shader validation. I don't know how to do this, but once I read the source code, maybe I'll find out. And so maybe I should do that to kind of bypass this issue, and then we can come back to this once we are done with like the more interesting stuff. Layers shader, great. So now we are, no, we need the exact same sources that were used to build the SDK, and it's so unfortunate that the SDK doesn't include this, honestly. It used to. I don't even know where to file this bug. Like, it's the sources should have been included, but they aren't. Okay. I'm gonna make a mental note to file somewhere a lunar G bug. Oh, actually, can I do this? I don't want to do this right now. So let's see. Layers were built with this tag. So then hopefully we can do git checkout this. Oh, git switch. That's the first time I'm seeing this command. Okay, let's do this again. It's so spooky that it doesn't happen every time. Okay. Okay. So now we have the correct source code, which is great. Oh, interesting. Oh. 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 So this is kind of curious, right? So this is not just a compute shader. Maybe it is a bug in our code, who knows. So this is not just a compute shader, it's a compute shader that uses specialization constants. However, I thought that we had to stop doing that. Wait, it's so tough coming back to the code that like, oh no, I see. Wait, I'm confused. Hold on. Right. Mm-hmm. So when we wrote this code, like a year ago, we used two variants of the compute shader for culling. You can go back to the occlusion culling streams from like 2018 and watch them. But basically, there's two passes for occlusion culling, and they use almost the same code, but not exactly the same code. And so initially, I used specialization constants for this, but then later I tried to run this code on AMD hardware, and there was a bug in drivers. And I don't even know, the bug may be fixed, the bug may not be fixed. I don't know. I don't have an AMD hardware like with me, right? So, but we applied a workaround, which is which caused us to not use specialization constants. But on the C++ side, we still use specialization constants. And so what happens is we create a we create a compute pipeline with specialization constants. And the validator in the debug layers applies them. Before validating the code. And so during this process, something goes wrong. This is so weird. Okay. This is why the problem happens when it does. So this is interesting. Okay. Oh. Aha. Aha. Okay, we found the bug in validation layers. I think. So I think what happens is that why does it happen randomly is something I don't understand though. But like, okay, I assume what happens is because we switched to Vulkan 1.2, we use some opcodes, we switched the shaders to Vulkan 1.2, we use some opcodes from Vulkan 1.2. However, during this specific process, we don't even use 1.2, or like the validation layers don't use 1.2, they use 1.1. And so I'm assuming that this should be 1.2. I still don't understand why this happens randomly, right? It doesn't like happen every time. It happens once out of like 5 times or whatever. And so that's still weird. That I would not expect. Yeah. So that's still unfortunate. Don't get it. So there is this grammar which is 1.1. Let's see what it looks up. 400. I don't know what this is. 400 is SPV op copy logical. Okay. So it's looking up this guy, and this guy is not like in the... It's not recognized as a valid opcode. Okay. This is what do you call this? Like, I didn't expect to go there. Aha, yes. So it is not able to recognize an instruction that was added in 1.4, in Spear V 1.4, which corresponds to Vulkan 1.2. So Vulkan 1.2 should be both 1.4 and 1.5 Spear V. And so the only thing I don't still understand is why is it random? Like, why does it sometimes happen and sometimes not happen? Is beyond me, right? Is there like a cache of some sort that like is occasionally kind of... Let's see. But okay, so I think we have enough information to file a bug on this. Because clearly, so this should use 1.2, and then if it did use 1.2, it would recognize the instruction, and things would be hunky-dory. I don't understand why it doesn't happen all the time. Like, I would understand all of this if it's just like, okay, 100% of the time the code breaks. The fact that it doesn't break 100% of the time makes me worried. But I don't want to, like, I mean, I don't care that much. It's like interesting mildly as to why this doesn't break all the time, but I don't want to go out of my way to understand that. To like, I just don't want to spend time on this right now. Okay. So, let's do this. Oh, this is the extension. Okay, never mind. Hold on. So, oh, okay. Visual Studio makes it really hard for me to copy this. So there's gonna be a bug link here, and we're gonna just say opcode. So we're just gonna say if the message contains these damning bit, we will just say we don't care, it's not our bug. What's the message? All right. Wait, hold on. I don't think yeah, there's no space here. I don't know how this happened. And now we will occasionally hit this weird thing. Oh. Alright, hold on. Clearly, you can't even copy things from the output window and have that work. So this should be... Oh, it's because when you paste something into Visual Studio's code window, it reformats that. And so it reformatted it to not do the right thing. Okay. Let's do this again. Okay, so we are hitting this validation error. It's not a real error. Okay. We are almost ready to proceed. Let me just file this bug. So, I still don't understand why it only happens occasionally, but I don't want to know, honestly. Let me just check that it doesn't look like it has been filed, so I'll just assume it hasn't been filed. So yeah, the only remaining mystery is why does it not happen like 100% of the time. But okay. We're almost there. So that's a thing. And we have a long-standing tradition to note bugs that we find during the development of this project, so we will do that. That's a very long title, but so be it. Okay. Let's proceed. I guess we don't need to print the shader hash stuff anymore. We can keep doing this, but okay. So where we are is we now, I think, have completed the first part, hopefully, which is we are trying to use the kind of core functionality whenever possible. We switched to the new SPIRV version. We hit a bug because of that. Our initialization code is a tiny bit simpler because we just create a struct that says, hey, we need all of these features from 1.2 and use that. So that's great. And we haven't started doing the actual like interesting stuff yet, but we are gonna do this now. Let me make sure that I don't want to remove anything else from this code before we proceed. Okay, I think this is fine. All right, so let's see. So the result is basically, let's see. there's like a bunch of changes here after the last stream because I had to. Some people reported bugs and I fixed them, and then I had to work around things like this with AMD bugs. So there's some changes here. But I guess technically this qualifies as day 15, even though day 14 was in November 2018. So let's just say that this is day 15, update to Vulkan 1.2. Updates to Vulkan 1.2. Note that we now require Vulkan 1.2, so you can't even run this code anymore on devices that don't support this, but I don't care. SpearV 1.5. And switches to from using extensions. Oh, the other thing is, let me actually check this. Let me finish writing the commit message for the functionality that's now core in 1.2. Not sure why. All right. We hit a bug involvation layers that we had to work around for now. So we use this feature called sampler filter min max, and this feature actually allows us to, in the shaders, like this guy, just do a texture sample. And to have that work, we must have used this min-max thing somewhere. And I don't even... How does this work? How does all of this code work again? Maybe it's in resources or something weird like this. Like somewhere we must be specifying the sampler. I'm confused now. Hold on. Depth reduce. Let's see. So when so there's this point. I'm not sure how many people watching this even remember anything that we do. But so there's this giant scene, right, that we render with like mesh shaders and all of that stuff. And we have this feature which is we use occlusion culling. And so to do occlusion culling, we render the depth buffer, and then I don't remember how to do this anymore. Then we generate a MIP pyramid basically where we reduce this depth buffer. And again, all of this is like, you can watch videos from 2018 on my channel about depth occlusion. And so we generate a MIP pyramid, and so to generate a MIP pyramid, we use the sampler min-max feature. And what sampler min-max feature allows us to do is when we sample in the shader, so we just say, hey, let me sample a point, right? And so what the GPU does is, instead of doing bilinear filtering, it looks at the 4 neighboring pixels and computes a minimum of them. But to compute a minimum of them, we must be setting something up to do that well. And how does this work? Right, so there's this depth sampler that we create. Okay. This is why I couldn't find this, because it's ext now. It was, so this was an extension, and now it's a core thing. So I just wanted to make sure that we don't use the ext bits if we can avoid that. It's really minor, it's the exact same constants. All right, so that is hopefully done. And this was kind of more complicated than I thought it would be because we hit bugs. But we now use Vulkan 1.2. Notice we didn't really change the code much, right? It's just, hey, let's update the constants here and there. Let's use a different version of SpearV. Let's not use a bunch of extensions that we were using before. So basically down like 4 extensions, right? We use 4 fewer extensions. Now we still have these guys. We don't really need this one, and we technically don't really need this one, because Should I just remove this? Because maybe I should just remove this so that it doesn't like kind of doesn't really occur in the code. And then at some point in the future we could rework this code to be cleaner. And maybe I could remove this one because at some point the code hit some bugs with Nvidia drivers, and I spent a lot of time trying to kind of, how do I put this, like trying to convince myself that the bug was in the drivers, not in my code. And so to do this, I used an Nvidia extension to diagnose, like this checkpoints diagnose thing, where it allows you to insert basically checkpoints into your command stream. And then if the GPU dies during rendering of your command stream, you can be like, oh, hey, what's the last checkpoint? But we don't really, like, I mean, if we hit something like this again, then I guess I'll keep this one. This one I technically could remove. Let me see if I should remove this, because although, now you know what, I'll keep this for now. Like, the story with this push descriptor stuff is that it's really convenient way to write Vulkan code, and it's also fast on Nvidia hardware, but it's slow on AMD hardware, and because of this, AMD driver doesn't implement this unless you use Linux, because on Linux there's two AMD drivers and one of them implements this extension. And so I was really hoping that this extension would end up in core, but I mean, this was introduced as an extension in Vulkan 1.0, and it's been Vulkan 1.1 and Vulkan 1.2, and this extension hasn't made it. So I mean, it's basically, it's never gonna be there, is what it is, which is unfortunate, but that's what it is. Alright, I guess I'll keep everything else as is for now. Okay, so our second task today is to merge all of the geometry buffers together. And so the hope is that it's gonna help us with the first task. Let me look at this, because I don't remember anything anymore. Meshlet data. And then vertices, and then indices. Okay. Sorry, I have to read my code from like a year and a half ago because I remember nothing. Why are there two of these guys? Who fills this thing? Aha, I see. Okay, I roughly remember this code now. So this is gonna require some surgery on this code. Let me briefly explain what are we gonna do now. So we are supporting two different rendering pipelines right now. Why? Okay. Microsoft Whiteboard. So we are supporting two different pipelines right now. I can run with mesh shading on, and then I can run, I guess, this. No. What's the key? Oh. Wait. If I disable mesh shaders, No. Oh, cute. If I disable mesh shaders, things break. Oh, 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 fantastic. I think we found more bugs. Today is a day of bugs. So what do I have to press? Do I have to press R? Why R? Because RTX. Why not M? This is weird. Okay. Oh no, this gets resolved. Yeah, okay. Hold on. So there's clearly a problem. Let's do this again. Okay, great. So I think we found one more bug. Somewhere. Okay, today's not a Vulkan 1.2 stream. Today is the day where we report Vulkan 1.2 bugs like everywhere. So here's what happened. So first, why do I use R to switch between modes? This is so weird. Why not M? Okay, so clearly this was written a long time ago. So we have two pipelines. One pipeline uses Nvidia mesh shaders. Nvidia mesh shaders are still not part of the core, right? So we have an extension for this. And by default, we use that because when we started the stream like a year and a half ago, one point was, hey, let's experiment with mesh shading. The experiments were great. However, we also support non-mesh shading pipeline for two reasons. One is we want to run on non-NVIDIA hardware. The other one is we want to compare performance between mesh shaders and non-mesh shading path on NVIDIA hardware. So we have two paths, and it so happens that in the non-mesh shading path, we use this thing, draw and direct count KHR, which allows us to submit draw commands to the GPU without knowing ahead of time how many of them there are. And so this is all great, and this all works, except I was like, this is a Vulkan 1.2 feature now, so I can do, oops, I can use the non-KHR version of that, and that breaks now. And so I'm not sure why that breaks. And so let's try to figure that out. So first let's run in release. In release we aren't using validation layers. Also we run like slower with mesh shading on now, but I'm not gonna investigate any of that. So we run fine without mesh shaders. Now let's try to switch to Vulkan 1.2 call. And we still run fine. So this must be a bug in the validation layers, I guess. I don't really know. Let's try to see what happens here. So when we switch to mesh shader, or to the non-mesh shading path, okay. Oh. Huh? Wait, this makes no sense. Maybe it's a bug in Vulk? Why does it even go through Vulkan DLL? Okay. Clearly there's many problems here. Oh, right. It probably goes through Vulkan DLL because the Okay, this is all kind of weird. So let's go here. So when the device is initialized, or rather when the instance is initialized, we created it with 1.2. And then Volk is a library that we use that loads extension functions and core functions and everything. And it's like saying, hey, let's load the pointer. Yeah, okay. Why does Control-C not work today? What's going on? So there is a pointer to this function that starts up as 0, and then we load it, and then the loaded function goes into the loader. But then when we try to call this function inside the loader, it crashes. Cute. And so this could be a bug in the loader, but it also could be a bug in the Nvidia driver, right? Like, it's hard to know. So yeah, I won't go into kind of what exactly happens here because it's complicated, but oh right, it couldn't be a bug in the driver because without validation layers everything's fine. So this must be a bug in the validation layers where they aren't like when they, so what the way Vulkan works is that every function in Vulkan, like this draw indexed indirect count, every function goes into a series of layers. And so like by default, maybe you have no layers loaded and then every function goes into the driver. But then when the validation layers are loaded, then what happens is the function goes into validation layer. The validation layer says, hey, let me check a bunch of things for you. And then let me pass the call to the next layer. And then maybe the next layer is a driver. And so let's disable validation layers again and then see what happens. And I'm assuming that what happens is the call goes directly to the driver in this case. Let us confirm this. So where's the call? This is the call. Oh no, it doesn't. So that's kind of odd, but okay. So the call goes to the Vulkan 1 DLL still. Somehow to a 2 instruction sequence, not a 3 instruction sequence, okay? And then it goes into the Nvidia driver. The reason why this says NVOGLv64 is because Nvidia still uses the same driver DLL for both OpenGL and Vulkan. So, however, when we use the debug layers, what happens is that it's really weird that we go to a different dispatch blob. We somehow go to a 3 instruction dispatch sequence, not a 2 instruction dispatch sequence. And then this guy just goes nowhere because oh, right, yeah, because there's a null pointer in the dispatch stack somewhere. Okay, so I think this is one more bug, but it's probably in validation layers, I don't know. Draw indexed indirect count. It's kind of odd that it's kind of odd. Like what I would have expected when validation layers are loaded is that we go into this guy, right? Because this is the function that says I need to do a bunch of debug validation for your call. Clearly it doesn't work. I think this is the... Yeah. So let's look at this thing. I'm not an expert in validation layer source code, so I don't know where to find all of these things. Name to func PTR map. Oh, right. Probably the problem is, well, maybe no. Yeah. So let's go here actually, and then try to debug this bit of code. In theory, there's like sources for all of this code, but in practice, I don't know where these sources are. What is even going on here? Why does it go through like 15 calls to figure that out? Okay, so I suspect that what happens is draw indexed indirect count, that somehow this function pointer map no. Oh. Wait. Oh, this is interesting. Okay, this is really complicated to explain. Yeah, R used to be an RTX switch, I think, because that's what I was calling this. So this is really complicated to explain, and I'm trying to figure out like which bug it even is. Like, what's the problem here? So it's like for this function, depending on how you get the pointer to this function, it either works or doesn't. And when it doesn't work, I don't understand if it's the problem with the Vulkan loader or if it's the problem with the Vulkan validation layers. And like it seems like it should be a problem with validation layers because if they're off, everything works, but I just don't know. So let me try to file an issue here. And like people who work on the loader work in the same company that works on the validation layers, so like it shouldn't really matter. Like as in I suspect that basically if it's a bug in the loader, like they will know, and I just don't understand. It's kind of weird. Let me see if there is no issue like this here already. Ah, so this is the same issue. So that's what I'm seeing as well. I'm just stumped as to why this doesn't happen when validation layers are off. Like I don't understand this bit. But okay, so we are actually hitting this issue. Like what is happening here is that I forgot to basically all of the Vulkan functions that we are using, they all are loaded through Vulk. And in Vulk there's like two ways to use Vulk. One is to load everything using the Vulkan instance, and one is to load functions that you can using the device. And so when you load using the device without validation layers, they usually go directly into the driver when you call them. Like for example, I'm pretty sure indexed indirect. I'm pretty sure that right now if we run without the validation layers, so like in release, right, and go here, then this point where we call the indirect count is gonna go like directly into the driver. Let's see if that's true. Yes. So we're not doing that. We were using the less optimal way to load Vulkan functions. I don't know why. Maybe I just forgot about this like a year and a half ago. And so yeah, this is the same problem, but it's not even for. Oh, this is in 1.1.130, not 1.2. Oh my. So it's basically the same problem, but not quite the same. But it works without validation layers. So maybe it's not the same problem, but it's a similar problem. And it's so bizarre that oh, no, I don't understand this. Okay. I suspect it might be a loader bug, but I just don't know. It might be a validation layer bug. It only happens when the validation layers are enabled, so maybe it's a validation layer bug. All right, so let me try to describe this in the issue relatively concisely, and then we'll move on with our lives, because we've worked around the issue by like using different loading sequence and stuff, so it's fine. Wait, get instance proc error. this thing called chassis something. Let me try to filing good bug reports takes time because you have to like be helpful and pretty precisely describe what's going on, because otherwise it's going to be impossible to, like, people will not want to even look at your bug because what does this mean? Who knows? Yeah. Come on. Visual Studio, work with me here. Control C. I think it's because of my Vim emulation plugin. Goes to Vulkan 1 DLL. They returned non-null function pointer goes to Vulkan 1 DLL. So this shim or whatever. Hold on. And like I have an inclination as to why this happens, but explaining this whole, I don't know if I'm right, and also I kind of don't want to explain this whole mechanism. And this shim crashes because the contents of come on, is a null pointer, so they jump to a null address. Yeah, this might be a bug in the loader. So I guess I need to say the loader was installed using. The fun part is the loader doesn't even come with an SDK anymore. It comes with a driver. So I can't even say, well, this is the loader that I'm using. I don't know which one. So using Nvidia Vulkan Control driver, beta driver. And let me see, maybe the version is like somewhere here. It must be. Okay. Well, I guess it's just the metadata for Vulkan 1 DLL says that the version is 1.2.1.31.0. So like it's not the case that we are not using the loader from Vulkan 1.1, it's just that there's some weird interaction between loader and validation layers and they can't even work together. Alright, so that's that. Wait, hold on. Load instance, load device. Alright, I think we are finally ready to actually work on like stuff that is meaningful. And yeah, I would not be surprised if it's a loader bug, not a bug in validation layers, but whatever. Okay, so we've worked around this thing. Fix the crash in non-mesh day 15 mesh shading path. Seems like a bug in validation layers or loader, not sure which one. Okay, so now let me see if there's questions to answer, and then let me actually start doing the interesting stuff. Okay, there's the render pass question, which I'm gonna cover a bit later. And there's no other questions. So let me go a bit further into like the actual stream stuff, and then I'll talk about render passes at the end. So, okay, a really quick refresher now that the code is actually works. So we have two paths. One is using mesh shaders, one doesn't. The path that doesn't use the mesh shaders is pretty straightforward. So there's the index buffer. And oh no, how am I gonna do indirect rendering? Well, at least the mesh shaders can work. Okay, we have index data and we have vertex data. So this is the non-mesh shader path. This is pretty straightforward. So the mesh shading path is a bit more complex. In the mesh shading path, there is no index data, and instead there is something else. So let me switch to the shader structs that I'm using for all of this. So instead there is this meshlet buffer, which basically for every like sequence of, what is it, 64 or whatever triangles, it's not 64 actually, it's like 64 vertices, and so it's like 100 something triangles. There's the struct that says the patch of triangles described by the struct has this bounding data and points to these vertices and these triangles. So this is called meshlet buffer. And then this is like a header, right, that describes a patch of triangles of some finite small size, right? And then the actual triangles are specified using the index buffer as well, but it's using really short indices. It's using like 8-bit indices. So if you look at the code somewhere that actually processes all of this data, well, you'll have to watch the original streams to really thoroughly understand this if you haven't, because it's a bit complicated. But in a nutshell, maybe on the C++ side there's code that is more readable, because in a nutshell I think it's just an 8-bit index buffer, more or less. Meshlet data. Oh, I haven't switched to... No, it must be 8 bits. Hold on. Right, yeah. This guy. Yeah, so basically it's just an 8-bit index buffer. And for people who work with computer graphics, 8-bit index buffer may sound weird, like how can you get away with just 8 bits? But the reason why you can get away with 8 bits is that each meshlet describes the indexing into the like each meshlet basically says here's 64 vertices and up to 128 or 126 here triangles, right? And so for each triangle you need to know which of the 64 vertices you use, but since there's just 64 you don't need more than 8 bits to represent each one. But then for each vertex you need to actually know where to fetch it from the large vertex buffer. And so this is how the data is structured. There's like an 8-bit index buffer, and then the actual vertices are pointing into the large vertex buffer. And so both of these are called meshlet data. And so there's like a meshlet data buffer. And then there's still a vertex buffer. And like technically you may not need a vertex buffer, because you could just pack the vertices into the meshlet data buffer and then kind of give up on some of the memory savings that we are using this for, but it doesn't really matter one way or the other. So this is what we use right now. So like we either use 2 buffers to render all of this stuff. I should say, I guess, vertex buffer. Or 3 buffers. And so in total we have 4 buffers, right? Because the vertex buffer is the same. Now all of these 4 buffers right now are 4 individual Vulkan buffers. And so what I want to do as part of part 3 is to refer to these buffers through a GPU side pointer. I haven't thought about this far enough ahead to realize that I can do the thing I want, but I can't do the thing I want for the non-meshlet path. Like I can only do the thing I want for the meshlet path. And so I'm not sure how that's gonna work. Yeah. Like I can merge all of this stuff. It's just that for the indirect rendering and bindless rendering and all of these good things to work, we will need to work without mesh shaders. We will still need one giant index buffer, which is not great, because then like you might as well have one giant buffer for everything else. Let me think about this for a bit, because I wanted to do this, but it's not clear to me what I'm gonna do with the old path, with the non-mesh shading path. Yeah. And if I'm gonna have a single giant index buffer to support the old path, then to do things like, hey, I want to load 5 extra meshes, I need to write an allocator. And then I might as well use this allocator for the other path. So it's not clear that what I want to do is even like interesting. Because, I mean, yeah. So that's a problem. That's a problem. And like I could say I don't care, because in the mesh shading path, what I set out to do is possible. But then like if I need to maintain the old path, it's gonna be painful. I could like not maintain the old path, but then my code will require effectively Nvidia hardware. Because right now this code actually, before the 1.2 update, it ran on Nvidia, Intel, and AMD. And after 1.2 update, I mean, if the drivers are supporting 1.2, it will. So that is not good. That is not good. But yeah, I don't see a way out of this. Like, if I am to support the non-Nvidia hardware, I will not be able to do the thing I wanted. or like I will not be able to do this efficiently. I can do this inefficiently, but that's kind of weird, right? Like, I don't want to lose a lot of performance. In fact, right now it's kind of interesting. Before, like a year and a half ago, and I'll need to compare. I don't remember the actual numbers that I was getting, but a year and a half ago on Nvidia hardware, it was faster to use mesh shaders, and right now, it is like slower to use mesh shaders. And that's the same code, right? More or less. And so that's unfortunate in general. But this means that even more so, I should preserve the non-mesh shading path as well as mesh shading path to compare them adequately. And like, I'm not sure why it's slower. I don't know if either path is slower than it used to be or faster than it used to be. Like, it could be the case that Nvidia drivers were optimized for like the old path, or it could be the case that they were pessimized for the new path because like there was some driver bug and it had to be fixed and it's now slower. Who knows? But to do this kind of analysis, I would have to go back to the streams from before and kind of look at what exact performance I was getting back then and then compare. And I don't want to do this now for sure. But so yeah, okay, so this says I do need the old path. I do need the non-mesh shading path. It's so interesting that the mesh shading path is not even faster, even though... Oh, did I... Hold on. Right, the occlusion culling is done... Oh, do I need these guys? I probably don't need these guys anymore. I do. Why do I? I guess GeoCell extensions are separate from Vulkan extensions. Hold on. Let me look at something real quick. Yeah, there's this whole like culling thing with subgroup ballot and stuff. And like, what? Yeah, so culling helps. It's just that it doesn't help enough. Alright. This is all weird. Okay, so we have ran a conundrum. The two things I set out to do. The merge geometry buffers is fine. I mean, like, we could do this. It doesn't matter. But the switch to GPU side buffer pointers only works for the Nvidia path. It doesn't work for the generic path. Man. Okay. And like, I can still do that, but it doesn't seem as useful. I was hoping that I can put the index buffer. I was hoping that I can put all of these buffers into one buffer. But then what I was hoping to do is that I could say, well, for each draw call, you can just specify where your mesh data comes from. And so yeah, I didn't realize that it doesn't really work for index buffer specifically. And yeah, there's like no way around this, I don't think. Damn it. Okay, I don't know what to do with this. I don't know what to do with this. And like maybe it's still beneficial to, yeah. So like the problem goes like this, right? What I was hoping to do is this. Nothing works exactly as it should today because I can't even zoom out here unless I guess, I think Microsoft Whiteboard was updated and it's not a good update. Okay. So what I want is this, right? So right now in our render, there's this draw sequence. So there's this draw 0 and draw 1, etc. And for each draw call right now, we specify the offset into one of these 4 effectively large buffers where the data is. For example, for the index buffer, I wonder to what extent this is really necessary, but okay. So for the index buffer, there's somewhere there should, yeah, so this is the mesh draw command, and there's like an index offset somewhere. First index, yeah, the first index. So there's an offset into these giant buffers. There's the first index, there's the vertex offset, and then for the mesh shading path, there's the vertex offset here, and then in the LOD structure, there's index offset and meshlet offset and all of this. There's like a lot of offsets into these large buffers, right? However, the question is, what if you want to load a new buffer? What if you want to load a new mesh, sorry? Or what if you want to unload an old mesh? And so with the way the data is structured right now, what I have to do is this. Here's a large buffer with all the vertices, for example, with all, because, so it's tempting to assume that we can only draw like one type of mesh because that's what we do right now. It's not actually true. We actually can do, what's this release? I think we can specify like multiple command line parameters. And so see, now we have 2 types of meshes. And so the way this works is all of these meshes are just stored in one giant buffer. Like not giant necessarily, because all of these both of these meshes are pretty small, but if we had more, right, we will need more data. And so what if you wanted to unload one of this mesh? Because right now what happens is there is 2 meshes here, and there's like a kitten here, and then there's a pirate here. What if you don't want to draw kittens anymore, so you have to unload kitten, and then you load some other mesh? Well, you have to put this mesh data somewhere. If it's exactly as big as the kittens data was, then maybe you just put it here, right? Instead of this. But what if it's bigger? Then you have to put it someplace else, and then you get fragmentation issues, and all of that's not great. So what I was hoping to do is I was hoping to create one buffer with mesh data, where we would store index data and vertex data and meshlet data and meshlet bits, which is all of these like vertex, index, like 8-bit indices and stuff like that. And there would just be a Vulkan buffer object with all of that, and then whenever you need to draw a different one, you just create one more object like this, and then you reference them dynamically from the GPU. And I think I can still do all of this, but just not with index data. And so this makes me sad. Oh, wait. Well, Well, yeah. There is like a way out of this, but the way out isn't particularly pretty. But yeah, basically I have to still make an index buffer for all of this. Okay. I don't know what to do with all this stuff. So let's do this. I'm gonna punt a bit on this whole problem, because I was kind of like hoping that all of this is gonna be doable, and maybe it's not gonna be doable. But there are some ways around this. And I'm not sure exactly which way I want to go. So let's do this. Let's do this. We are going to temporarily say we don't care about this stuff. Let's change the plans. However, what we will do is we will experiment with this, because I still want to understand, like, does this even work? This is why I wanted to make the stream in the first place. There's a new hardware feature and a software feature, and I want to know, does it work, right? And like, is it fast? So I still want to know. And so for me to know this, I would still like to try to do something here. It's just that this something can't quite work exactly as I was hoping it would. But maybe that's fine. Maybe that's fine. So although like merging geometry buffers is still somewhat beneficial, because right now there's this weird place. Yeah, you know what, merging some of the stuff is still good. It's still beneficial. Okay. Because right now we are using like 3 to 4 buffers for all of this stuff. And it's kind of good for code clarity though. It's just not great for necessarily efficiency or... Yeah, man, I don't even know what to do. I'm kind of disappointed because I thought that it would just work out, and yeah, I forgot about the index buffer specifically because I was so focused on the mesh shading path. I forgot that there's some special properties for some of this stuff that don't quite work. Does this still work? It still works, okay. Oof. Oof. So I still kind of want to know if this GPU buffer pointer stuff works. But it just doesn't seem as important as it was at the beginning of the stream because I still need a giant index buffer. Let's see. Yeah, I don't know. It's basically not interesting at this point because I can't deal with the index buffer stuff. And so because of this, I don't need GPU side buffer pointers anyhow. Yeah, I'll have to think about what to do now. What to do about all of this. So I don't want to do any kind of rash things now. I don't want to go into like, yeah, let's merge all of this and then it's like I don't have a way out, so I have to undo all of this. I don't want to go there. Let's do this. So it's kind of stupid and simple, and there's no reason at all for us to do this at this point. But since we are here and since we got Vulkan 1.2 running and all of this, let's just see if GPU side pointers even work, and then defer everything else for later. And so probably the easiest way for us to do this is maybe we'll keep all of this geometry rendering stuff as is for now. And maybe the easiest way for us to do this is this. So we have a compute shader right now that performs object calling. So like right now we have a lot of meshes that are outside of the frustum, and we have a lot of meshes that are occluded because we have occlusion calling on. So like right now we have we are drawing like 52 million triangles on screen, but if we disable occlusion calling, we are drawing 100 million triangles on screen. So we have a complex compute shader that calls a lot of this geometry out. And this compute shader right now needs access to a few buffers. Specifically, it needs access to 2 buffers for reading draw calls and mesh data, because it needs to read the draw call data and then say, well, these draw calls are visible. Then it needs to fill the draw commands, because for this frame it needs to say, well, we are going to render these visible meshes, right? And then also it uses this draw visibility buffer for, I think, complicated occlusion calling algorithm that, not complicated, but like interesting occlusion calling algorithm, let's put it this way, that again, you will have to go back to the old streams and watch them. So I guess at this point I'm kind of just curious, can I just stop binding some of these buffers and load the pointer to these buffers through uniform data that we use? And maybe we should just do that, because yeah, I don't want to do anything else right now, because I don't want to commit to anything else right now, is the better way to put this. So the way that you're supposed to be able to use pointers on the GPU is like this. There's this new extension called GLEXT buffer reference, which is the GLSL extension. And so when you use this, you can declare what's called a buffer reference, which is like a pointer to a struct type. And then you can put the object of this type into anywhere, basically. And this object is just a 64-bit integer, and then on the CPU side, you can get this integer from anywhere. I don't know if you can write to this thing. I would assume it's read-only. But it would be interesting actually if you could write to this thing. So let's first see kind of what kind of shaders even compile with this stuff. Hold on. Or I guess we could actually do this with this guy, maybe. but it's probably easiest to do this with the coloring shader. So let's see here. So we're gonna require this extension, and in theory what this allows us to do is to say here's, and we don't need like pointers inside structs that we point to or anything like that. We kind of just need something like this. And I'd like to understand what we can do with this. Can we, for example, can we cast a 64-bit integer to this guy and then just use that? That would be useful to know. So what I want to do is this. First I want to know if this shader even compiles. I guess I can do all of this from Visual Studio. It does. And if I disable this, presumably it stops compiling. Okay. So then my question is, oh, I guess I'll have to, hold on. Like right after the struct, we're gonna put block type, let's call this draws. Or is that ambiguous? Wait, what? Yeah, okay. Let's call this draw pointer. So that works. Now inside this pointer, I'm gonna have an unbounded array of draw structs, and so this works as well. And so the question is, what if I want to replace this guy with something else? So what if I want, instead of binding the buffer where I'm reading draw call data from, I'm just not gonna do this anymore, and instead I'm gonna say, what's the best way to do this? I guess I'm just gonna say draw pointer draws. Is that how this works? Okay, so that compiled. So then my question is, can I copy pointers? And so this is not like just like a general, like the syntax is a bit weird, right? Because it's all GLSL, and like you have to have this complex expression to even declare a pointer, but it's basically a pointer to a struct. And so if you wanted pointers to other structs, you'll have to have more types. But I'd like to figure out what can I do with this object, because maybe we can do the thing I kind of wanted to do, just not like all at once. So that works. Then the real question I had is, can I do math on this pointer, right? So like, can I add 5 or 1 or whatever? And so the answer is no, I can't. What if it's an integer? So what if it's a 64-bit integer? Wait, hold on. 64-bit integers are not supported in GLSL. Interesting. Let's see. Oh, maybe only signed 64-bit integers work? Because this guy must... I guess I'm confused. Hold on. So there's a syntax error at line 30. Yeah, so I can't use a 64-bit integer. But if I enable this extension, I can. So how does that work? The reason why I wanted So, I mean, I want pointers, right? But I also kind of want pointer math, because if you don't have pointer math, it's like painful to do some things. And so even if I have this guy, I can't declare... How is that possible? Can I just not do this? I'm confused a bit, hold on. Yeah, so clearly you cannot use 64-bit types, but there is this extension that introduces extra functions that work on 64-bit types. And so these two statements together don't make sense to me. How can you not use 64-bit types? Does it depend on some other extension? I don't get it. Let's see. Oh, maybe this is the extension that I need. Okay, maybe this is the extension that I need instead. Okay, so this is better. Now, I think there was something here about convert. Buffer reference types can be constructed from a UN64T value. Okay, so maybe then what I can do now is I can do this, and this works. Cannot convert from something to like temp reference. Cannot convert from to. Maybe it's an explicit cast that I need. Maybe not. Oh, maybe this is how this works. Okay, so I think this is saying that maybe I can use the 64-bit integer type as a pointer, right? And then whenever I actually need to access this pointer, I can convert this pointer to the type that I need, and then access data through that. And the syntax for this is all kind of obnoxious, right? It's like, for every struct that I need to access, I would need to declare something like this, which is not great. But it's better than having nothing. So let's call this mesh draw array instead of block type. Okay, so now we aren't using the buffer at all. We are just using this pointer. But right now, if I were to run this code, something horrible would happen. And I'm not sure if the stream would like explode, because what I'm expecting right now is I'm not passing a pointer to this shader, but I'm using a pointer in this shader to read data from it. And it's like an array, right? And so something bad will happen, clearly. Because effectively, okay, I'm now worried about alignment here. Hold on. Let me just move this. I'm gonna put it like this just in case. Yeah. Okay. Something doesn't compile now. Right. Okay, let me put it back here for now. The reason why I'm squeamish about all of this is that the alignment rules in shaders are complicated, but we now use Vulkan 1.2, so maybe we can fix that as well. Like, what I think happens right now is that on the C side, there's like a padding here, and then there's a UN64T draw pointer here. So I think that's what happens. All right, so should we just try to run this code, like, and watch the GPU explode? I don't know. I'm worried that it will cut the stream and the driver will have to restart, but I guess if it has to happen, it has to happen. So like, I'm gonna press F5. Maybe what happens is the GPU crashes and the stream terminates, because I'm not filling the pointer at all. Or maybe I get validation error, and oh yeah, see, I just get a validation error. It's all good. All right, yeah, so I'm starting to use 64-bit integers. And so, oops, I clearly need to enable that. What's this feature? Is there a feature for this? Or can I just not use this? This must be a feature somewhere. Is it here? Wait. Aha, okay. It's a feature in the base line. Oh, interesting. And I'm not enabling this for some reason, but I definitely should. Okay. Okay. All right. So thank you, Nvidia, for making a driver that survived the abuse. We haven't died. Like, everything still works. The problem is that the GPU has hung, right, or crashed or something, and what's VFI? Yeah. Somehow we didn't print. Oh, maybe we did actually. Hold on. Yeah, okay. Actually, this is the case where the NV checkpoints that I was adding before at some point help. So we know that we started to run the calling code because there is a checkpoint, and I think this checkpoint is before, or actually interesting. Yeah, I think there's like two checkpoints. I think this says the command has been processed by the command processor, and this says the command has been executed by some future stage. And so the command processor has parsed our called command, which goes right after the calling code. But the calling code has not finished executing, and then the calling code tried to reference a pointer, and the pointer is null, and like, things explode. Cool. Okay. So to actually have this code work, though, we need to pass the pointer to this buffer in the struct somewhere. And so this is the struct, and we need to say call data dot draw pointer equals something. And so how do we get the pointer? The way we get the pointer is there is this vk get device buffer address. Get buffer device address. I don't know. Get buffer device address. So we need to say what device. Oh, and of course, okay, we're gonna make a helper for this because If we're going down this path, we will use this all the time. So we'll make a helper get buffer address, where we need to pass basically a buffer object and device. So it's gonna return the key device address, but I think this is just a pointer. And so we need to pass a device and the info, buffer device address info. So this is the usual Vulkan is verbose, so we need to do structure type buffer device address info. Great, and we are just gonna pass info buffer. Okay, and then return this. I'm not sure if this guy can return an error. If it can, we should probably assert that it doesn't. Let's see. I mean, I guess we're just gonna assert that it's not 0. Or, yeah. All right, so let's get back to this thing. And I think we have a buffer called db for draw buffer that has the draw commands. So we're just gonna use that. And let's put a breakpoint here and see if that worked. Oh, right. So for this to work, the buffer has to be created with a bit saying, hey, we are gonna need the address of that buffer in the future. So wherever we create the draw buffer, don't know where it is. Aha, here. We need to say buffer usage create device address. This guy. Okay, that still doesn't work. Oh, and the memory has to be allocated with a special bit. I've never used the CNAM before, so I don't even know where to specify it. Oh dear. Oh my god. Okay, great. Ah. Oh. I see. Oh, this is like interesting for multi-GPU, right? Because I want to have a pointer to the buffer data that I can dereference from the GPU, but I have two GPUs. I need to say which GPU the buffer pointer should refer to, I guess. Okay, but I get it. This is the case where we need to have this guy. And I guess if the usage has buffer usage shader device address bit, then we need to perform some special kind of setup saying we need we need the flags to say vk memory allocate device address bit. And I guess we need the device mask to be 1 because this says it's a bit mask. And we only have one device, so bit 0 refers to the only device we have. So I guess that's what I have to do. I don't know. Okay. Okay, so we got a pointer. It's a 64-bit value. And then our code still doesn't work. So now we have to ask why, and the answer is I don't know. I suspect the answer might be like struct layout doesn't work as I thought it does. Okay. All right. So that's a good first step. We now use the pointer to the buffer data, and we are still binding the buffer, but we don't really need to anymore. So that was easier than I thought it would be. And I like the fact that when the buffer pointer was 0 effectively, like the GPU didn't die. Everything was fine. I mean, I got a device loss, but that's fine. Okay, so that worked. Let me look at the calling code again. And so this is interesting because this means that it looks like pointer arithmetics basically sort of works. Where's this shader? Because I mean, I just got a 64-bit value, right? I could say like plus 15. I wonder if GLSL has size off. Clearly size off is not a thing that's implemented in GLSL, which is going to be a problem actually for any code like this, right? But I could say like plus 5 minus 5, and it's kind of weird, but it's like whatever. And so it's just a 64-bit value that I can change and then dereference the results from this. So like in theory, what I could do, for example, is, and I don't think I should be doing that, it doesn't really matter one way or the other, but if I knew the size of mesh draw struct, and I could compute that, so this is 16 bytes and this is 16 bytes and this is, I'm probably aligning this, so this is probably 16 times 3, so this is 48. So because I know this is 48 bytes in theory, I could just say, well, I'll call this draw array, and I could say, well, my draw call is at an offset 48 times the draw index. And so this is now a pointer to just one, oh, come on, just one draw call. And so I'm just gonna have one throttle here. I guess it's not an array anymore, so that's weird. Well, whatever. And then instead of accessing di here, I'm gonna access 0. So I basically converted the array access to like pointer arithmetics here. And that probably still works. Okay, that still works. So that's interesting. So at this point, I'm trying to figure out what's like the best way for me to work with this in terms of GLSL syntax long term, because this isn't like too bad, given that I can just convert kind of 64-bit integers to the pointer value here. This is not too bad. Can I... Let's see what the GLSL spec says. Like, the syntax definitely isn't, you know, I would have preferred if I could just say something like, you know, mesh draw pointer, right? Something equals a 64-bit value here, right? And maybe this, I wouldn't be able to do pointer arithmetic of this type on this type directly. I don't really care about this as much. It's just that having to declare a GLSL type for each unique value that you need to be able to read from pointers on GPU is not very user-friendly. So that's something I'll have to figure out later. Because effectively this guy says there's like a buffer reference thing, but to use a buffer reference, you can't use it on variables. You have to use it on blocks, on buffer blocks. And obviously there's no templates in GLSL, right? So you can't say, oh yeah, I just want a type that is like a pointer templated on T that stores T inside this buffer reference thingy. So yeah, you basically have to manually make your own type for each use, which isn't awesome. Can I do... Is it always a buffer? Like if I just had one structure here, presumably I would have to say draw dot mesh index. I can't say just dot, right? Like if I were to remove this, it would not compile. Yeah, because there's no field like this. And so it's almost as if, yeah, it's almost as if like, in addition to things like that, I basically need the exact same struct, just like stored in a buffer, which is weird. I can shorten this to like V, right? So this would be like mesh draw pointer. And then this guy is draw array. And then I just say mesh draw pointer draw. Mesh draw pointer, draw array. Can't do size of, which is not great. But then I just say draw.v everywhere. And that's just a shorthand essentially. Effectively .v is like the reference in this case, right? And so that works probably. Okay. Okay, so from that part, I think we're all good. This is kind of what I was hoping would be possible. So except for the syntax that could be better, everything else seems fine. I can declare a pointer, a pointer type, and then I can take a 64-bit integer, I can do arithmetics on the 64-bit integer, then I can convert the result to a draw pointer, and then I can just dereference this draw pointer, and this would read the data from the GPU memory. And I have to create it in like special ways, but that doesn't seem too bad. And so in this specific shader, right, it doesn't seem to be worth it to do this in direction, right? Except that, I mean, I could like convert all of these things to buffers and maybe my code gets simpler, but because of the syntactic issues, my code doesn't actually get simpler when I do this, right? My code gets like more weird, and then it doesn't really get more or less verbose, I don't think. So, and then I think you can't, I think this is a read-only construct. Let's see if that's true. Can I just say like draw.v.mesh index equals 5? Does that work? Oh, that works. Oh, I did not expect this. Wait, what? Okay, hold on. So, interesting. So, I mean, we shouldn't do this because, I mean, something will break. So now we only have kittens and we were supposed to have like kittens and pirates, I think, right? Oh, no? Hold on. Okay, so you can write to these guys. Maybe you can't? Let's see. I don't... I'll believe it when I see it. So we have kittens and pirates, and now we are overwriting the thing with 0. Okay. I don't think that's what... Oh, right. This is actually fine because... Yeah. Like, you can't just rewrite mesh index. There's like some cached variable in this draw call structure. Anyway. So writes work. I did not expect this. Okay. This is interesting. So I have this buffer here with the draw command count. And other buffers with like draw commands and stuff like this. Does it mean like I don't need any of this stuff anymore and I can just, let's just try to see what happens if we convert all of this stuff to pointers. Just to see what happens, right? So we have draw array, mesh array, draw command array. We'll need a whole lot of pointer types. So this is, I think this is basically the biggest issue here. Like we are doing this right now to see if this can work. But the issue is the code is like verbose. And so we'll keep depth pyramid and we'll keep it at at index 5 for now. Now we'll have to have a lot of types. So we need a mesh draw pointer and then we'll need a mesh pointer. And then we'll need, what else do we have here? Draw command pointer. Wait, mesh draw command. And so for example, draw commands we write to, right? Whereas all of this stuff we read from, and then these guys are read-write. We both read and write from this. So then we have a draw command count. Draw command count is just a draw command count pointer, I guess. This is just an integer. And then the draw visibility. So draw visibility is interesting. This is the case where I'm guessing the alignment also here actually is not 16, it's 4. So draw visibility pointer. And then there's also just an integer here. Okay. And I guess let's just try to convert like the entire shader to work with this. I don't know. So And there's just 4 bytes for each visibility struct, and now we can refer to this as V. Like, the problem now is that, so I'm using an extension, a Visual Studio extension to highlight my GLSL source code, and of course this extension doesn't understand all of these new features, right? So now everything will just be highlighted as like syntax errors, which is not super friendly. But let's just convert all of this and like see if it works. So instead of mesh, we're gonna have a mesh pointer, I guess. And this is gonna be mesh array plus mesh index. It's unfortunate that the size of doesn't work. So mesh, oh wow. I mean, assuming there is a padding here, which you don't know if there is. Let's look at the C++ code. Interesting. So for now, let's do it like this, because then this is 16 bytes, this is 16 bytes, and this is 8 times 16. So this is 10 times 16, which is 160. All of this is obviously super fragile, right? Like without size off, it's not actually easy to do this. So I won't like commit this code. I just want to understand, does this code work? Like, can you do this, right? This is kind of why this is what I wanted to figure out in the first place. Can you do this? Okay, let's see. 158. Right, so the draw command count is not a thing. Draw command count pointer, draw command count. Let's do it like this. Okay. So far so good. So this is just mesh.v, I think. And now we need this draw command thing. And now we need to know the size of this guy. So this is 1, 2, 3, 4. So this is just 32 bytes. Draw command pointer. And then this is just .v. Okay, our shader compiled. And now we just need all of these guys to work. Okay, so I'm just gonna copy this here. I might be going over the size of the push constants at this point, I'm not sure. Let's see, this is MB. And all of these buffers will have to be created with the appropriate bit, right? Because we need basically all of them to be accessible through a pointer on the GPU. And I think there was one more mesh buffer. This guy. What? Wait. What? What? So this code doesn't compile. What? What do you mean it doesn't take one argument? I'm passing 2 arguments. How? What? Am I hitting some weird? No, like what? What the hell? Okay, I don't know. I can't explain this. Whatever. Maybe there was some weird like Unicode symbol or whatnot. Alright, let's try to run this code. Maybe it works. Oh, hey, the code works. So what we have just done is that we've moved all of this like buffers to pointers. This means that instead of specifying all of these as descriptors, we don't need to, we just need to pass our texture in as an input. And then here we need to say that it's the only resource that we use now, and presumably that all still works. Okay, cool. And I think the calling time was 0.04 milliseconds before this, and it's 0.04 after this, so there's no like speed penalty, at least in this code for us. Okay. All right, so I want to end the stream here after like answering questions and stuff, because effectively, so we've converted to Vulkan 1.2 and that went well. We had to file a few bugs for this. But then I was hoping to do the same thing that I was doing now for our like geometry pipeline. But then the issue is that, and like it's very, very clear that we can do this now, because we've just used pointers and pointer arithmetics and all of this stuff, and all of this stuff worked. So that's great. The big issue is that the point of doing all of this was to merge all of the buffers into one buffer and then pass the pointer to this buffer with each draw call, so that each draw call could say, well, my mesh data lives like here, right? And so for this to work, the index buffer has to be part of that, but it can't be, because we don't read the index buffer in the shader directly. And so that's the snag, right? And like maybe we still decide that it's kind of all worth it, and then we'll just like, it doesn't matter. We'll figure something out with the index buffer. Like for example, maybe with the index buffer, the right approach is to merge dynamically the index buffers for only meshes that are visible in the frustum, which there's fewer of them, and then like dynamically create a large index buffer on the GPU, and then we can still do everything the way we want it. It's just there is like one place where we have to copy the data, and we don't need any of this for the mesh shader path either. But if we don't do that, it's not clear kind of why we would merge the buffers. So I guess let's treat this stream as we converted to Vulkan 1.2, and we played around with GPU buffer pointers, which they mostly worked. This was, I mean, they basically worked. There was no issues here. And so like the only issue is this syntax is obnoxious, right? Like it would be really nice if instead I could just use like mesh draw pointer in the place where I need it, right? Like it would be really nice if I could say effectively this. Let's, I don't know. Maybe it has to be some syntax here that's not that. But like I would be fine with saying, okay, like pointer to mesh draw, right? Pointer to mesh draw. And then instead of .v, I would just say like draw arrow. But the big thing is I wouldn't need all of this stuff, right? And so having to declare all of this stuff is a bit painful. But it works. There's probably some preprocessor trick, right? I can probably wrap this in some macro and then just say, well, like I need a pointer to mesh draw here, right? I could literally do this, I think. Let's try this. Buffer reference, buffer type, pointer, alignment, type V, right? So I could literally say pointer mesh draw 16, right? And then pointer mesh, oops, 16 pointer. Oh, except that like here, it's fine, right? So pointer mesh draw command 16, and then effectively pointer like uint, right? 4. So if preprocessor works, which I'm assuming it does, well, it doesn't. Oh, no, wait. Okay. And then here I can just say uint pointer for this guy, right? Oops. And then here there's going to be a uint pointer. And here there's a mesh draw command pointer, not a draw command pointer. And I guess this is kind of closer, right? Because instead of an arrow, I have to say .v. And I still have to pre-declare the pointer types, but at least it's like one line for each. And so that's fine. The inability for the syntax highlighter to understand any of this is not great. So like working with the shader is becoming more and more painful visually, right? The more pointer features I use, which is not fantastic. But that might just be solved with the updated extension. And then the size of is a problem. Like, so yeah, so this is the one bit that is not really good. And like, you don't need to do this, right? The When I started converting this code, I just used an array inside of the pointer buffer, and that doesn't need manual kind of address arithmetic, pointer arithmetic. So maybe that's not a big deal. Anyway, so I think the gist of it is the pointers work. It's not clear what exactly we want to do with these pointers though, right? Because, yeah. So what I want to do is I want to commit the code that added support for pointers effectively. So like this guy and the resources code. And then I'm going to punt on what exactly we are going to do with pointers. And then we'll figure it out later, right? So this is day 15 pointers, or like GPU buffer pointers work. It's not clear what we want to do with them exactly. So for now, just add functions to work with them. All right. So let's add this here, and let's end this here. Let me briefly look at the code. Not at the code, at the questions. I'm sure I can change pointers based on the based on anything. Yeah. Ext buffer reference tool. It's hard to compute the size of with a macro, right? Because of like the rules are really painful to like. I really don't wanna. At this point, if I want to compute the size of, I need a compiler, right? Like I could certainly fork GLSlang and implement like actual pointers there. It doesn't seem like it's that painful necessarily, at least for a hack for sure. But yeah, when I started this, right, like you can do. I guess effectively you can do this, right? And then instead of a pointer, you can say like array, and then instead of the manual, like literally I could do this. Hold on. So I could say I want an array of like these mesh draw structures. And then here I could even use this type. I don't need to go through the, I only need to use the 64-bit integer if I need to do arithmetics on it, right? So here I could say, oh, I need a mesh draw array. And here, wherever I say draw, right, I could be saying mesh draw mesh draw array dot VTI, and I think that's the same thing. Well, yeah. I moved the like I'm just reading. I could do this. Yeah, here I just moved the point where I read the data to like reading into a struct. So now I need to remove this. But like point is, I don't really need size of, right? For things like this, I could just declare a type that is an array of things and then create a pointer that points to the base of the array and then use the indexing and it kind of computes the size of for me. It's just not like it requires you to have two different distinct types in some cases or something like this, right? Like it's not quite the same thing. Yeah, I'm not sure what xbuffer reference 2 means. If it's a typo, then oh, it's not a typo. Huh. All right, so there's another extension. Let's see. Oh. Ah. Uh-huh. Okay. I see. I see. Right, so this is interesting. So this is saying that if I use the reference to, does our code still work, by the way? Okay, good. So this is saying if I use reference to, then instead of doing this stuff, oh, actually, let me undo the things I was just doing now. Okay, so this should still work, presumably. Okay, so I can actually do pointer math on these guys directly. So effectively, instead of doing this, I could say, well, this is the mesh drop pointer, right? And then I can just say plus di, presumably, and that works. Oh, hey. All right, so this looks a bit more like pointers on the GPU. So now I can use mesh pointer here and mesh draw command pointer here and qint pointer here and here. And so I have to remove all of the manual address math that I was doing. Okay, so that's much better. And also, yeah, I guess you can implement the size of this way, which is cute. This is kind of how you would implement offset of in C, right? And so this is how I guess you implement size of in. I guess this is how you can implement size of in C without having the size of operator, right? Not that we need this now because there is. With that extension, there's actual pointer math. Okay, so with that, basically the only minor annoyance, right, is that we have to pre-declare the pointer types like this, and then whenever we dereference them, we have to say .v dot instead of like an arrow. But that seems pretty minor. Okay, cool. That is much more interesting. Thank you, Christoph. All right, so there was only one question that actually there were two questions. So there was an off-topic question and an on-topic question. The on-topic question is, it's now possible to use indexing for UVs and even normals GPU side instead of just vertex positions. Well, so you can do this without the mesh shaders. We actually do this when we use the traditional rasterization pipeline. For example, this is our vertex shader, like on a non-Nvidia GPU, the way our code works is by using this code. And so you can see that we just have a buffer, and this is still using the non-pointer buffer, but we can certainly convert on all of this to pointers now. Which, yeah, maybe we will do. I don't know. I need to think about basically what fate the pointers will have in context of this project. But the this access is just like you can do. You can in the vertex shader you just have GL vertex index as an input, and then you can read everything else yourself from buffers. However, and like you can do so. Right now we read. The vertex data from just a vertex buffer using the vertex index, but nothing says that you should do this. Like you could say, oh, I'm gonna read normals, like I'm gonna read every other normal from the vertex stream, right? And nothing happens because we don't use the shader, but if you switch to the shader, you see the normals are weird, right? Well, the kitten is kind of interesting now. And so you could do that before mesh shaders. And there's some interesting tricks that actually leverage this technique. For example, if you wanted a separate position index buffer versus attribute index buffer. You can't do this. Like, the API doesn't really give you a way to do this. But if you use 32-bit indices, and say you split them into 16-bit low half and 16-bit high half, then you can say, well, index is just a number. Whatever number you put in your index buffer will be reflected in this variable. And so you could just say, well, like, the low half will have the position index and the high half will have the like texture coordinate index. And I'm just gonna index them like this, right? And like this, and it'll all work. So you can do this before. What mesh shaders give you is an ability to access. Mesh shaders give you a bunch of things, but in the simple context, they give you an ability to access triangle data. Because mesh shaders don't work with vertices, they work with meshlets, which is essentially a triangle patch. And there's actually a not here. So, like, in theory, and it's a bit complicated to do some of these things because the way the data is prepared in this code is it's using kind of optimally packed meshlets, and it's not very easy. You can access the triangle data pretty easily, but you'll have to, let me see here. Yeah, like if I wanted, for example, to output the per triangle normal in the fragment shader, it's not as trivial to do this here, unless I use some other features of mesh shaders, which I don't want to go into. But you can access data for all vertices of a triangle, and even for vertices that the triangle doesn't belong to necessarily, in the mesh shader. Like, as an example, there is this feature that we occasionally use for debugging, which I don't remember what it even does. Oh, right. It takes the index of the meshlet, and then it converts it to the color, right, by just computing a hash function, and then it outputs this color. And you see this is kind of a visualization of how individual meshlets are constructed in each mesh. Everything that's the same color is the same meshlet, so it's the same group of triangles. And so things like that are much easier to do with mesh shaders. But yeah, you don't have to have mesh shaders to actually like read triangle data yourself or anything like this. Yeah, right. So if you have memory issues with because of the vertex UV unrolling, then like you don't have to. Yeah, you don't really. I don't think even you need mesh shaders for this. Maybe they help. I don't even think they help too much, to be honest. So, for example, if your biggest issue is you're suffering with the memory pressure because you have a lot of UV seams, right? And for some reason you need what I would say is, right, like, you could look at your vertex data, because if you have a vertex data, you can pack the position into 2 bytes per attribute usually, unless precision is not enough. Maybe precision is not enough, but you can segment your meshes so that precision becomes like reasonable. So ideally you would be like, this is actually what our vertex structure looks like. If I go back to the structs here, well, okay, no, we store floats, we store positions as floats, but like you could store positions as 16-bit integers, Vx, Vy, Vz, right? And then assuming you still need normals, you store normals as 8-bit integers, so you have nx and y and z and like some padding field, right? And then you have float 16 t to utv, say, or also 16-bit integers, and maybe you need padding here. So like, point is, maybe your vertex is just too large right now, but assume you can't reduce the size of your vertex, and assume, or you tried it, it's not enough, you still can say, well, in my vertex structure, I'm just gonna have 2 integers. One is gonna be the vertex the position ID, and then one is going to be the text code ID. And this is kind of similar to what I was talking about just now with the index buffer trick, but the index buffer trick relies on you to be able to pack both of these IDs into a 32-bit integer, which maybe your meshes are so large and you can't segment them into smaller pieces or aren't willing to, and so it's just impractical. Okay, that's fine, right? So do this, then each vertex is just 8 bytes, and then you can have two separate streams. One is with position data, one is with texture coordinate data. And then if you manually fetch your vertex data like this, then effectively what you will have is, okay, instead of using this code, I'm gonna say position equals position array, position buffer, let's say, right? Which is indexed using the position index I'm reading from the vertex, right? Which is just an integer, and then you're gonna have like here something like positions position buffer, right? And so this kind of thing is really easy as long as you're not relying on the fixed function vertex fetch. And you can do this and it will save you memory, right? You still will need to create unique vertex UV pairs, but each pair will cost you like 8 bytes, right? And then the actual more expensive data is going to be in separate buffers. So if you want, you can do this, doesn't require mesh shaders. Like mesh shaders make some of this packing easier, and they enable some types of this packing that aren't possible without them. But I think in this specific case, if you want memory gains, you can probably get memory gains that are really close to what you would get with mesh shaders, but like without mesh shaders. But yes, like it's definitely the case that the mesh shader paradigm removes some of the restrictions that used to exist, right? I'm just saying, like, I think in your specific problem, you don't have to go all the way to get most of the benefits that you want. But yeah, like in the middle of the stream, I was like, oh my god, I don't even know if I can do all of this things that I planned because of the index buffer. And then the mesh shaders is not the problem. There's no index buffer. You can just do what you want. Anyway, yeah, and like, so yeah, so there was a question about the subpasses, and maybe we should save this for another stream because it's been basically 3 hours. But the short story is, with Vulkan, there's this trend of, there has been this trend of, structuring your render as many subpasses inside one big render pass. And so there's a couple of problems with this. One is it's mostly relevant for mobile GPUs. It's not really relevant for desktop GPUs. And even for mobile GPUs, it's a bit complicated. There are some mobile GPUs that don't use the setup that allows them to benefit from this kind of setup. But then it's harder to structure your renderer in the way that it actually can leverage all of this like render pass, subpass structure if it's not purely a Vulkan renderer, if it's a cross-platform renderer that doesn't just run on Vulkan API. If you want a dynamic render pass configuration, like let's say there's an effect that you want to enable or disable dynamically based on whether it's necessary or whether the user settings are set up a specific way or whatever, you need many different render pass configurations, and so managing this becomes painful. And I think in general, my point of view is render pass subpass structure is built a certain way, and the reason why it's built a certain way is it tries to abstract the kind of details of what's going on in hardware in hopes that driver can leverage this to be efficient. Like some drivers can run, on some architectures you can run one pass and then have this pass output pixels to render target and then have this render target be processed in a fragment shader without incurring the memory cost of writing this render target and reading this render target. And like Vulkan said, well, let's abstract this and then have the drivers be able to do this. And the problem with this is many things that you might want to do aren't possible with this model, even if they're still possible on this hardware. And B, very often drivers fail to take advantage of this in cases where like you would expect them to. And so I guess I'm like not a fan of this approach on any axis. I think it obscures important hardware details. It relies on the drivers to do really, really complex, smart optimizations, and drivers often aren't actually able to do this. And it makes it much harder to make a composable renderer, and it makes it much harder to make a cross-platform renderer. And so, from all of this perspective, I guess it's just like, yeah, I'm not a fan of subpasses. I think very few people are, from what I know. I think there are people who like understand subpasses as a necessary evil, and there are people who think of subpasses as an unnecessary evil, right? I'm not sure there's a lot of people who think that subpasses are a great, fantastic feature that is like, you know, that is magnificent and this is how things should be. I definitely don't think so. I think they're simultaneously not sort of, yeah, they're like not declarative enough, they're not user friendly enough, they're not rich enough, they're just like, it's too much complexity for too little gain is how I would describe it. All right. And yeah, as Christoph is saying, like mesh shaders allow you more freedom for sure. So let me give you an example actually that is somewhat topical here. And depending on how much memory pressure you have and all of that, it may or may not be as interesting. But so a project that I'm working on, right, occasionally is Mesh Optimizer. And one part of this project is actually vertex data compression. And the reason why vertex data compression is interesting in Mesh Optimizer is, well, I want a compression algorithm that can be reasonably efficient for vertex and index data, but can be really, really fast. Because, like, the reason I care is, imagine you have an SSD, and SSD can read, good modern SSDs read data at like 1 gigabyte a second or something. And so if your decompression algorithm runs at like 10 megabytes a second or like 100 megabytes a second, it's faster to load uncompressed data unless your compression is like, I mean, regardless, if the speeds I'm quoting are the output speeds, like output megabytes per second, not input megabytes per second, right? So like regardless of how fast your, regardless of how good your compression is, if it decompresses at 100 megabytes of output data per second, it's going to be worthless on an SSD. And so the codecs that I am working on, they decompress on one core of a CPU. They decompress at 2 gigabytes a second. Like they decompress at 2+ gigabytes a second on my CPU, which is pretty good on a single core. And this imposes some restrictions on the compression. But some of these restrictions are very compatible with the meshlet approach. So like for a meshlet, basically what you have to say is, here's my meshlet, which is 64 vertices, let's say. You can technically do more, but let's say you say it's 64 vertices and up to 126 triangles. If you can take this block and then compress this block using restrictions that allow you to write a decompressor that is efficient, it doesn't have to do like complex, like Huffman like tree lookups and all of that stuff, then you can probably decompress it in the mesh shader. Like I think with the, you can't do this directly, because with a mesh shader what you want to do is you can't decompress the entire vertex buffer. You have to decompress one meshlet, right? But I think it's doable to take the codec that I'm using for both. Index data is a bit complex. So index data might need, actually, yeah, so index data would need a bit of adjustment, primarily because it's just not decompressible in parallel on like, the restriction of what you have to do meshlet decompression is your algorithm has to be able to decompress a small set of data like at once, and B, you want the decompression code to be able to run on 16 to 32 threads, let's just call it 32 threads at a time, because otherwise you're not efficiently utilizing the hardware, because the hardware works in groups of like 16 scalars at a time. And so yeah, index data I'm not sure, but vertex data I think you could probably change the codec that I'm using a bit and make it work in context of like meshlet data decompression, and it's gonna be like not ultimately as efficient as it could be on in terms of hardware utilization, but like close enough. So yeah, you can do things like this, but I strongly suspect that in your specific use case, simpler methods are gonna get 80% of the memory reduction of memory savings, and it's gonna be good enough. Anyway, all right. So I guess that's it. We didn't quite do the whole kind of shebang of like converting the vertex pipeline to use GPU pointers. I think it's very, very clear that it can be done. I think the only issue is index buffer in the old pipeline doesn't work like this. So I'll think about that. And we spend a bunch of time kind of tracking 2 bugs down. And we filed all of these 2 bugs, so that's good. Maybe they are going to be fixed at some point. I've pushed all of this to GitHub, so you can kind of... I didn't push... I'm gonna take the pointer stuff that we were doing and push it in a separate branch. GPU buffer address. I don't think we are gonna use this code directly. Like this code, we used buffer pointers in a place where they make the least amount of sense, because it's the place where it's easiest to experiment with this stuff. So I'll push it in a branch just so that the code is on GitHub, and we will see what happens to this in the future. All right. As always, it's been a pleasure streaming, and we might do this again if I figure out what to do with all of this buffer pointer stuff going forward, or maybe we'll do some texture bindless stuff at some point in the future. We'll see. Anyway, thank you everybody, and see you later.